So you've heard me talk a lot about the deviation from ideal behavior. Gases don't typically follow the ideal gas law. There are many instances, most of them, where the ideal gas law just breaks down, does not work well, and we need to use other models to describe the gas. And I'm sharing with you here some of the most commonly used non-ideal gas laws, or not laws, models. And there are a variety of them, and they're used for different applications at different times. The first one here is the virial equation of state, and it is an infinite expansion, sort of like what you see in calculus with Taylor series. And the implication of each of these coefficients, A, B, and C, is significant from a physical chemistry point of view. And if you ever take any advanced courses in physical chemistry or in polymer physics, you will no doubt see A, B, and C, specifically B and C, when discussing polymers and how they dissolve in different solvents. But that's besides the point. I'm not going to ask you about the virial equation of state in this class. Another common one is the Redlich-Quang equation of state, and that's the latecomer. It came around in the 1950s. It's one of the last models to be widely accepted, and it is a pretty complicated beast as it looks, right? You could see here the letters A, little a, and little b, and you can also see this here in van der Waals, A and B here and A. Those are correction factors that are specific to each compound. So you have to go to a table of Redlich-Quang coefficients, and for helium, say for example, and look up what these numbers are, and it will tell you what they are. And you could use this specific equation for helium. If you want to use it for hydrogen, you have to look up A and B for hydrogen, which would be different from that from helium. So that's the shtick here. It is true here and it is true here. The A and B here are not the same. Here for van der Waals, I'm going to go to a van der Waals table and look for A and look for B and see what they are for specific gases that I want to use. So those are the ones. The van der Waals is what we're going to focus on in this class. Don't worry about the first two. Just worry about the van der Waals. The van der Waals is one of the first corrections to the ideal gas law. As you can see here, you basically have P plus a correction factor times V minus a correction factor is equal to nRT. So it's very similar to P equals nRT. Here you have a little bit more of a complication, but it's similar. But this is the most commonly used one. I encourage you to look in the textbook. They explain how van der Waals came up with it if you're interested in sort of the history of it. It's interesting. It's very short. I think it's like a paragraph to read. And it is, I'll tell you from my own experience, I did not use van der Waals very often when I tried to model gases. I don't think it's a great model. Gases that follow the van der Waals equation of state are often known as van der Waals gases. Gases that follow the Redlich-Quang equation of state are known as Redlich-Quang gases, and so on and so forth. Ideal gases are very uncommon, and you really have to get to situations where the ideal gas behavior is emulated. So, for example, we talked about how for ideal gases, the molecules ignore one another. Well, if I have a gas inside of an aerosol container, you bet they're not going to ignore one another because they're so close together. So an aerosol gas, likely not an ideal gas. But if I were to take the gas in the International Space Station or something like that, where it's very sparse, I would see more of an ideal behavior, or at least PV equals nRT is easier for me to understand or to model my gas. One last thing I want to mention, you might ask, then why the heck are we using PV equals nRT if it doesn't work? Well, from an engineering point of view, it gives you a nice, quick, and dirty calculation without having to deal with these nasty equations, right? So let's say I'm trying to come up with a design for I don't know, a new container for gases, or a new spaceship, or understanding what happens to gases in a submarine as it submerges into the bottom of the ocean, or for a spaceship that goes up to space, or any of these things. And I don't feel like plugging it into these terrible equations and figuring it out because I have a whole bunch of different gases that go up and down, and maybe I have some CO2 because people are breathing CO2 out, and I have extra oxygen because I'm trying to, whatever, it gets complicated. And so I have to get A and B for different oxygen and for nitrogen and for carbon dioxide and maybe from argon, and I had to figure out the ratios between them and blah 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 blah. That would take me forever, and I would spend days and days in Excel trying to figure it out, if not a more complicated modeling system. Then I can just spend 5 minutes plugging into P because I see what happens. Now, that's not going to give me the number that I want, but it's going to give me a direction. It's going to tell me, oh, well, if I increase this and I decrease this, this should happen in theory, right? So it'll give me a direction, right? I'll know, for example, if I told you, if you eat 1,000 McDonald's burgers in, I don't know, 12 hours, you will gain weight, right? I just know you will. How much? I don't know. But I know, I have an idealized equation in my head where I just, weight is equal to extra food. So that's how that works. It just gives me an idea of how things behave. Anyway, enough of me yapping around. So let's look at an example of a van der Waals equation of state being used. Okay. Sorry about that. There we go. And here, I'll do this here on the whiteboard. And what I want to do is I'm going to calculate for you, we're going to calculate together the pressure for an ideal gas and for van der Waals gas at the same time and compare them side by side. So calculate the pressure exerted by 1.00 mole of SO2, sulfur dioxide, at 0 degrees Celsius, and having a volume of 22.41 liters. And part A would be if it is a perfect gas, and part B would be if it's a van der Waals gas. Van der Waals gas. And if it is a van der Waals gas, I will need to give you the A and B, right? Because these A's and B's are not something you can just calculate. Well, I mean, you can, but you won't in this class. 6.865 liters squared. And look here, the A and B that I'm giving you will inform you as to which R you should probably use, because they have embedded in them units. So this one is going to be liters per mole. B is not going to give you much because you always want to have, well, that gives you liters. So it will give you liters. A will give you liters and ATM. So you probably want to use the R that has liters and ATM. And if you go look at that table again that I shared with you, R is going to be equal to 0.08206 liters ATM mole K. All right. Now, because this isn't a whiteboard, I apologize. I wrote all the units here for you here. When I plug it into the equations, because I have a whiteboard that's very small, I'm going to omit the units. So I will point them out as I do that. Okay. So for part A, this one is, we'll do this in red. So for the contrast, here P is equal to nRT over V. Okay, so let's plug that in here, substitute it in here. Okay, and I give you the fact that it's 1 mole. I give you 0 degrees Celsius, which means you have to convert it to Kelvin always. And that's pretty easy. This is 273 K. Right? And I give you liters and I give you moles, so you have to convert anything else. Just the fact that this has to be 273 K. So to get P is equal to 1 mole. Look at me not omitting units. Aren't I just the greatest? 0.08206 liters ATM mole K. This is 22.41 liters, and all of this is being divided by, oops, not 22.41 liters, it's 273K. Apologize, 273K, and this is 22.41 liters. Okay, and if you were to substitute all of this into the calculator, you'll find that this is 1.00 liters ATM. So it gives you 1 ATM. All right, that's not a number. ATM, it's 1 ATM. Okay, 1.00 ATM. We have 3 sigfigs. All right, so that's how you would do the ideal gas, the perfect gas walk. The van der Waals equation of state. Let's put that down here. I'll write the van der Waals equation of state for us here. Thusly, okay, it's just, this is the pressure conversion factor. This is the volume conversion factor. And this is going to be equal to nRT. Then we're going to solve for pressure. And it's going to be nRT over V minus NB minus N squared A over V squared. And I'm going to substitute everything in, and then we're done. 1.00 mole, 0.08206 liters ATM, mole K, 273. This is a little bit complicated to do on a whiteboard, but it literally is just plug and chug. Liters minus 1.00 mole, and then this B thing, which cancels out my mole, becomes liters, so I can subtract these two, and B is 0.05679 liters per mole. Okay, this thing here, this whole thing is just this. Now I have to subtract minus 1 mole squared, 6.865 liters squared ATM mole K divided by 22.41 liters squared. Okay? And if you were to put all of this in, I'm going to just for the contrast go for red, and you get that this is 0.989 ATM. And you can follow through here, you can see all the units cancel and you get ATM. So you can see if I use van der Waals, I get that is 0.989, and here it is 1.00 ATM. So it's not exactly the same.